Hello everyone, welcome back to the inflection point. In this video, we are going to see how the idea of limits gives the whole branch of calculus. We will just see the intuitive idea behind limits. So what are limits? Basically, limit is that fundamental concept on which all the concepts of calculus are based. I am repeating this again. Limit is that fundamental building block on which other concepts of calculus are based, right? So the concept of limits was derived, or it was developed due to two major geometric problems. The first geometric problem which gave rise to introducing the idea of limits was the tangent problem. What is this tangent problem? Suppose you have been given a curve. This is x-axis, y-axis, and you have been given, let us say, this type of curve. Okay, this curve, and there is a point P. Let us say the coordinates are x, y, and there is a tangent like this. There is a tangent like this. Okay, so this red line we say is a tangent, right? So the problem which we say is a tangent problem, the problem is basically finding out the equation of this red line, equation of this tangent line, right? This was the tangent problem. I am just defining. Okay, and the second problem which gave rise to the limits concept is the area problem. Again, what is an area problem? You have been given a curve like this, and this time we are interested in finding out the area bounded by this curve f between two values a and b. Okay, so basically this shaded portion, we are interested in finding out this area. So this was the area problem, right? Although area problem is more ancient than the tangent problem, and when I say it is more ancient, so I'm talking about 1000 years back, right? So mathematicians were dealing with this area problem 1000 years back before the tangent problem. And tangent problem, basically the mathematics behind or that developed after this tangent problem, that was developed by Newton and Leibniz, okay, which we now say is the differential calculus, right? So later on, once the concept of limit was developed, the whole mathematics after the tangent problem was developed by Newton and Leibniz simultaneously, there was a connection that was established between the area problem and the tangent problem. For the 1000 years, mathematicians were finding out the area under the given curve using different methods. Once this limit concept was introduced and its mathematics was developed, there was some connection that was found out between both these problems, both the area and the tangent problem, right? Once that connection was established, a new branch of mathematics was developed, which we now say is calculus. Okay, so basically calculus consists of two parts, as you should know or you must be knowing. One we say is the differential calculus, and the second we say is the integral calculus, right? So the mathematics behind the tangent problem, that mathematics is now known as the differential calculus. So the maths behind this differential calculus is basically based on the geometrical concept, which is the tangent problem. Okay, so mathematics or calculus based on tangent problem we now say is the differential calculus, and the area problem deals with or is dealt by integral calculus, I should say. Okay, so there were two different names given, and combinedly they are known as calculus. Okay, Area problem we will discuss later on when we learn the integrals, right, in later part of this course AP. So first let us start with the differential calculus, and let me introduce the idea of the tangent. Okay, so basically what is a tangent? The question is this. So now from our previous knowledge we have learned that if there is a circle, let us say, with the given center, and we know that any straight line which meets the circle at a single point, that is called a tangent, right? So this green line, it is meeting the curve, this circle at a given point P, whose coordinates are, let us say, x comma y. So we call this as a tangent. And what is the definition? That it meets the curve at a single point. Okay, but this definition is not complete or is not proper. Why it is not proper? Because it only applies to the special curve which is a circle. What about other curves? For example, if I take a curve like this, okay, and there is a straight line like this, okay. So according to our previous definition, that any straight line which meets the curve at a single point, we call this as a tangent. But here, as you can see in the B part, this was A part, this is B. In B part, you can see that this straight line is also meeting the curve at a single point, and obviously we cannot call this straight line as a tangent. Okay, we can say that a tangent is a line which touches the curve, but what is the mathematics behind this saying that how you will say that a curve is touching or not? Okay, there is another curve, let us say this one, and there is a straight line at this point. Suppose it is intersecting or meeting the curve at a single point here. So this black line, we can call this as a tangent, but again it is not meeting the curve at a single point. Okay, it is intersecting the curve at multiple points. So what is the correct definition of tangent? Right? That was the basic problem. First we should define the tangent, and then we will develop how to find out the equation of the tangent, which was our tangent problem. Right? So in order to obtain the basic definition of tangent, we should look at the tangent in some different way, right? Using some different perspective. What is that perspective? Let us see. Suppose you have been given, let us say this is y-axis, this is x-axis, and a curve is given to you like this. Sorry. Okay, there is a point P on this curve. This point is P, and I'm calling, let us say, their coordinates as x comma y. Okay, and there is another point Q on this curve whose coordinates are, let us say, this is x1, this is y1, and this is x2 comma y2. Okay, now a straight line which is passing through both these points P and Q like this, we call this straight line as a secant line. This line is, we call as a secant, okay, which is intersecting the curve at more than one point, right? It is not touching the curve, so that line is called a secant line, right? Now the idea is, what if I bring this point Q2, not Q2, it should be Q only. What if I bring this point Q closer to point P? And let us see how geometrically this affects the straight line, this tangent or this secant line. Okay, so let me bring this point Q nearer to point P. Let us say here is your Q, or I should call as Q dash. What about the tangent? Now, not the tangent, what about the secant line? This now secant line will look like this. Okay, again I am moving this point Q dash closer to point P. Let us say the new position of Q is this Q double dash. right? And what is the position of the secant line? The secant line will look like this. Okay, now understand this very carefully. Here is the moment which Newton developed the whole mathematics behind the gravity and the change in one quantity with respect to other quantity, change of the acceleration as we increase the altitude and so on. So this was the very basic idea, right? What was that idea? That I'm bringing this point Q closer to point P, and there will be a certain point. There will be a point which is very closer to point P. If you can see here, this point I'm calling this as, let us say, Q triple dash, right? And if I join this point P with Q with a straight line, so this secant will now appear to you as a tangent line. Okay, so what we are basically doing is I am bringing this point Q closer to point P, right? And you can see what is the effect of this movement, or what is the effect of this anti-clockwise movement of point Q, or this anti-clockwise movement of the secant. This secant is basically becoming the tangent line, right? It is just touching the curve at a single point. Okay, and this gives the basic idea behind finding out the gradient of the tangent, because please remember this, that we were interested in finding out the gradient of the initial tangent line. Okay, remember the tangent problem, we were interested in finding out the equation of the tangent line. So we know the point, but we do not know about the gradient of this the tangent line, right? So basically we are interested in finding out the gradient of the tangent line, right? So what we can say is that this tangent to any curve is basically the limiting position, or I should write this, that tangent is the limiting position of the secant line. And by saying this limiting position, what I mean is that when this secant, this point Q, becomes closer to point P, point Q is moving closer to point P, meaning point Q is just about to overlap point P. So this secant is becoming a tangent, okay, like this. So this movement, this anti-clockwise rotation of this secant line, it is becoming a tangent at a certain point, and that point is called the limiting point, or the limiting position of the secant, as this point Q is very, very closer to point P. Okay, practically how we can see the concept of limit is that you must be driving your car, your motorcycle, or anything, two-wheelers, right? And there is a maximum speed which is written on the speedometer. Let us say you have a car whose maximum speed is 200 kilometers per hour, right? So practically we try to move closer to the maximum speed, which is 200, but we never approach the limit 200. Okay, sometimes we can approach to 195, we can even approach to 196 or 7, right? But not exactly 200, right? So we can say that 200 is the limiting speed, or the limiting value of the speed. Okay, actually we are not exactly moving to the speed 200. Okay, we approach to a certain value. Similarly, this secant line is approaching, this point Q is approaching closer to point P, and once this is done, the secant line becomes the tangent line, and this idea changes the whole branch of mathematics, and all other branches also developed. I mean, the application of this concept, limit concept, developed the idea of differential calculus, and then later on that calculus, differential calculus, that was applied in various other subjects also, right, where the change of one quantity now can be measured with respect to other quantity. Okay, here we can say that the y coordinate is changing with respect to x coordinate, which is the gradient. Okay, now we are in a position to find out the gradient of this tangent line by finding out the gradient of the secant line, and then finding out the limiting value of that gradient when we move point Q closer to point P. Okay, so this was the idea of tangent or the tangent problem. Now let us take one example and try to find out exactly the equation of the tangent line. Okay, so let us say we have one example that we have been given a curve y is equal to x square and there is a point P at 1, 1. Okay, so quickly let us sketch this curve. This is y, this is x, and the curve is this. Let's draw it more wider. Okay, for example, the curve is like this: y is equal to x square. This is y, this is x, and there is a point P at the curve at 1, 1. This is P. Coordinates are 1, 1. Okay. We are interested in finding out the gradient of this point, of the tangent at this point. Okay. So, as we know, the equation of a straight line can be given like this, that y minus y1 is equal to gradient of that secant line into x minus x1. Why I am calling the secant line? Because there is a point Q. I will develop the tangent using the same idea that we have discussed just now. Okay, let us call this point as h and 1 plus h. Okay, because this x coordinate was 1 and we have increased this point to h, not 1 plus h. Sorry. Let us say this is 1 plus h and then 1 plus h whole square. Okay. Now let us draw the secant also. So as you can see, this is our secant PQ. Okay. Now what I will do is I will move this point Q closer to point P. Okay. So moving point Q closer to point P like this, and let us see what it how it will affect the shape of the tangent. Not shape, but the orientation of the secant. So if the point here is Q, here is the point Q, the new position, the tangent becomes like this. Not the tangent, secant. Sorry. Okay. So as you can see, if this point Q is very close to point P, it becomes very difficult for you to identify which one is tangent and which one is secant. So I should say that this secant becomes the tangent at point P as you move point Q closer to point P. Okay, and moving point Q closer to point P means that the x coordinate I am reducing. This x coordinate was 1 plus h, so it simply means I am moving this 1 plus h closer to point 1, meaning I am putting h equal to 0. Fine. So the basic thing is we need to find out this gradient of the secant. So as we know from the basic formula of the gradient, that it is change in y over change in x, right? So change in y is, let us say, 1 plus h square. Okay, or I should take this point as 1, 2, 4 only. Okay, this is 2, 4. It is just nearby the point P. Okay, so change in y meaning is change in y over change in x. Yes. So delta y is x square. Let us take this as a general point, not 2, 4. Let us take this as x and x square. Simple. Okay. Any general point x, and the value of the y coordinate at x is x square. So change in y meaning is whatever is the y coordinate at point Q, this is x square, and y coordinate at point 1 is 1. So change in y is x square minus 1, and change in x is x coordinate was x. So I should rub here as rub this 1 plus h. It is just x. Okay, so I'm moving from x to 1 right? Meaning I'm moving from point Q closer to point P. So change in x was x minus 1. Final point is x, initial point was 1, so change in x is x minus 1. So basically I need to find out the value of this expression at x equal to 1. Why at x equal to 1? Because this gives the gradient of secant, which is change in y over change in x, right? I need to find out the limiting value of this secant. Limiting meaning when this secant will become tangent. So secant will become tangent when at point x equal to 1, when you move closer and closer to point 1, so that there is no difference between the point P and Q, right? So as you can see here, when we put x equal to 1, we have now an expression x square minus 1 over x minus 1, and pay attention very carefully, because this is the idea that we will see. We will solve some questions, not some question, very vast type of questions in limits chapter, how to find out the limits of any function. So now consider a function here which is in front of us in the form of x square minus 1 over x minus 1, and we need to evaluate its value. And what type of value? Its limiting value. Why I am saying this limiting value? Because at x equal to 1, this function is not defined, or it is indeterminate, because numerator becomes 0. The moment I put x equal to 1, this becomes 0 by 0. X square is 1, so 1 minus 1 is 0, and 1 minus 1 is 0. So 0 upon 0, we say it is indeterminate. Indeterminate form means its value can be anything. It is not defined, it is indeterminate, right? So at x equal to 1, actual value of the function we do not know, but using some concepts of algebra, we can find out that to what value this expression or this expression will approach as we move closer to point 1. And this is our basic intuitive idea, moving point Q closer enough to point P, meaning moving closer to the coordinate x equal to 1, not at exactly equal to 1. Okay, so how we can predict this value? So using algebra, we can write this as x square minus 1 using x plus 1 into x minus 1 over x minus 1. And remember, I am finding out the limiting value. I am finding out the limiting value of gradient of secant, right? So at x just tending to 1, right? So when x tending to 1, now we can say that x is not exactly equal to 1, so these two factors can be cancelled out, and what I remain with is just x plus 1, right? So we can say that as x is approaching to 1, the value of this secant, gradient of secant, is approaching to 2. And what is this limiting value? This is basically the gradient of the tangent. So this whole thing, limiting value of secant when x tending to 1, can be replaced now by the gradient of the tangent. So gradient of tangent value comes out to be 2. Now it's just a piece of cake to find out the equation of the tangent, which is y minus y1 is equal to 2, which is a gradient mx minus x1. So here we have y minus 1 is equal to 2x minus 2, meaning 2x minus y is equal to 1 is the equation of the tangent. So this was the tangent problem, which was solved, you can say, by Newton and Leibniz by giving the whole idea of limits. Okay, moving a point closer enough to a given point such that there is no difference between the x coordinate, and in that case the secant becomes the tangent. Okay, now you are in a position to find out the gradient of the tangent at any point of the curve. Okay, we will develop this idea more when we will actually solve some questions of limits, and then introducing the idea of differentiation. There also we will use the first principle of differentiation in which the limits were introduced. Limits will be used, right? So this was the tangent problem. Now let us quickly turn to the area problem, right? The second problem was the area problem. So as I told you earlier, that one function is given to you like this, and we are interested in finding out the area under this curve between the points A and B. So what historians were doing is, not historians, what ancient mathematicians were doing was that they were dividing this area into a number of rectangles like this, right? Rectangle number 1, rectangle number 2, rectangle number 3, and so on. And what they were doing is they were just adding the area of these rectangles. But as you can see that this rectangle is not exact. Okay, if you actually draw the rectangle, you can find out this type of error will always be there. This is the error that will always be there. So you cannot find out the exact value of the area, right? But yes, you can move closer to the actual value of the area. Why? Because I can even increase the excuse me, I can even increase the number of rectangles. Okay, so if you increase the number of rectangles between the given points A and B, you can even move closer to the actual value of the area, right? So how the concept of limits we can see here. Okay, so what is the area, actual area? We can say that area, actual area of this curve, actual area under this curve is the limiting value of all these infinite number of areas, right? You keep on increasing the value of, not value, you keep on increasing the number of rectangles, and the moment you get a very, very large number of rectangles, so that those becomes infinite, so that you cannot make a difference between these separate rectangles, it becomes continuous. So that is now the limiting value of all those areas, addition of limiting value of all the addition of those areas. So here again the concept of limits was introduced, right? So this was the area problem, that was the tangent problem. These two combinedly gave rise to the new branch of mathematics, which is calculus. One was called the differential, one was called the integral calculus. So that's it about the intuitive idea behind limits. We will formally start the chapter limits in the next video. I hope you enjoyed. Thank you so much.